Okay, good morning and good evening if you are from the US. Thank you for coming today. It's a great pleasure to have Professor Evelyn Tang from US University to speak here today. So in my mind, Evelyn is always a very legendary person. Did her undergraduate study in humanity and literature, but in her last year of undergraduate study, she discovered that physics is very interesting. So she decided to pursue a PhD degree in physics at MIT. Then she went to MIT and became a PhD student of Professor Xiaogang Wen. During her years at MIT, Evelyn did a lot of interesting works on topological states of matter with Professor Xiaogang Wen and also Professor Liang Fu. Then after her PhD study, Evelyn decided to change her research direction again. So she started doing biophysics. And I think even now as an assistant professor at the US University, Evelyn is still doing biophysics. I think one unique aspect of Evelyn's work on biophysics is that she applies ideas from topological states of matter to biophysics, which I think is also the main topic today. Let's welcome and Evelyn, please.
Thank you, Eugene, for this very nice introduction. And indeed, I think you will see in my talk that I do bring pieces from my past that comes together. And I would love to hear your thoughts also on this work that I'm going to present. So let me start with the motivation why I think that topology can be interesting for biology. And if you look at a brain network, let's say your brain network or my brain network, you see that it looks quite messy, quite heterogeneous. There's a lot of, looks like random cellular firing. And yet underneath all of this heterogeneity and randomness, clearly the brain network can support functions that are very similar amongst individuals. I can talk to you, we can regulate our bodies, etc. And so I'm very curious about this emergent function, how an underlying network can support function that's much more than the sum of its parts. And in fact, that this emergence can even be, in some sense, robust, even despite underlying heterogeneity, randomness, etc. Of course, emergence is a big topic that we have in physics and in biology. There's lots of many different and very interesting emergent behaviors, things that are often long length scales, long time scales. Today, I'm going to focus on activity that's long time scales, for example, circadian cycles or memory, that these persist despite consisting of many faster underlying reactions. And for physicists, understanding these kinds of systems are particularly challenging because statistical mechanics typically assumes particles to be identical. Often we understand things much better in the equilibrium regime. And here you can see that we've lost the assumption of identical particles. These are systems are often functioning out of equilibrium. And so how can we still understand these very fundamental and important emergent functions, such as that which regulates our bodies and life around us? So what are some examples of these different kinds of emergent phenomena? So today I'm going to be using the example of a global clock here. And of course, you see this in many different places in gene replication that happens by growing and shrinking of these filaments, or even moving, let's say, like in this leech. Again, this is some kind of emergent behavior where many parts act together to produce more than the sum of each part. And what I'm going to show you today is that these different behaviors can actually all hinge on the edge state of a topological phase that is very non-equilibrium, that consists of many non-reciprocal cycles. So what does this mean? I had said that in biology, biological systems are fundamentally non-equilibrium. And so here, this non-equilibrium comes about because we eat food and we store up chemical fuel in our bodies in the form of ATP and GTP. And this fuel is always being used. So this is a very typical cycle in the body. It has a phosphorylation reaction, so adding a phosphoryl molecule, and then this molecule is removed. And so it goes right back to where it started, and that's why these cycles were called futile cycles. So sort of futile, they're useless. Why is it that it seems to consume so much energy because this is expensive to go this way and to come back. It's pumping a flux through the system. It's not just in steady states. It's not just in detail balance. In fact, instead, there's a flux going through the system. And so this consumes a lot of energy, but yet it looks useless, futile, because it comes right back to where it is. And biology has so many of these kinds of motifs. And you would think, usually biology exists in a regime of scarcity. There's not enough food. So why is it that we would be consuming so much energy all the time? And so here, our work proposes a way in which these wasteful-looking motifs could have a purpose, which is to stabilize and provide robustness for the system. And so I'm going to show you more what I mean by showing you a model using these phosphorylation, dephosphorylation reactions in a model for circadian rhythm. And so to show that robustness of oscillations comes out from that, I'm going to be showing you underlying topology and some features. And then I'm going to be discussing the necessity of non-Hermitian systems and also new applications. And I also want to really invite the audience to ask questions anytime throughout my talk, because as Liu Jun was saying, I'm really bringing in different ideas from different places. And so I just want to make sure that everybody's on the same page. So I'm going to be pausing along the way to make sure that people can ask questions. And so at those moments, please feel free to jump in. So let me start with...
Sorry, can you just
Hey,
give... Hi. Can
Hi.
you just give an example of a futile cycle? Excuse my ignorance, but...
Oh, yeah. So what I was saying is that this is some kind of a molecule, and then you add a phosphorylation, like a little phosphoryl group. So, a group that has like a phosphate group on it, and then you remove it. And this is being actively pumped. So it's a cycle. Yeah, it's not in detail balance.
Okay, thank you.
Sure. And that's a great segue into the model, because our model consists, the model consists exactly of these kinds of adding these phosphoryl groups. So here we have the possibility on this molecule that has 6 monomers to form a hexamer. You can see that on each monomer, there are 2 possible phosphorylation sites where it could undergo an orange phosphorylation or a pink phosphorylation. So here we add a pink one, here we add an orange, here we remove a pink, and here we remove an orange. And so that these are basically two futile cycles times 2 for orange and pink. And you can see that the numbers of each phosphorylation is given in these numbers in the brackets. So the first number is the number of orange phosphorylation molecules. The second number is the number of pink molecules. And so here we have this cycle clearly going in this way. And we can describe the state space of the system as being composed of these 2 numbers, the phosphorylation level. At the same time, for each phosphorylation level, you can see that the system has 4 choices. It can either phosphorylate in either the orange or the pink, or it can dephosphorylate in either the orange or the pink. So these 4 choices can be laid out as follows, where we have these choices, and we can allow for what happens, these choices to be then denoted using this subscript here, so that the state space consists of 2 numbers and this letter. And then what this means is that then for each phosphorylation level, such as 2,1, we can have 4 of these different subscripts. And then here we allow for transitions between them that go in the opposite direction. So here you can see this goes clockwise, this goes counterclockwise. And what this means is that for each phosphorylation level, there's actually these 4 states, and these actually form a unit cell that can then be repeated across the whole space of phosphorylations. So this would look then like a lattice, in which then you have a unit cell consisting of 4 states. These 4 states are then repeated. Here, as we go along this horizontal axis, this is increasing in this orange phosphorylation. Here, as we go in this vertical axis, we're actually increasing in this pink phosphorylation. And here we have, these changing in phosphorylation numbers given by these black solid rates, and then just changing the internal state of the system is given by these gray rates, and you can see that both of these cycles are in the opposite chiralities.
Sorry, just to make sure. So here, each side of this lattice represents a physical state of this system, of this
exactly.
System.
Yeah. So yeah. Mm-hmm.
Then what determines the size of the entire lattice?
So yeah, let me just clarify your question. So So exactly. So each state or each of these sites is a different chemical or mechanical state. So chemical because these are different chemical reactions that change between the different sites, or it can even be mechanical. So here this circle is switching between a circle configuration to this diamond configuration. So it could be a chemical or mechanical configuration. And so this is essentially configuration space that makes up all the different sites of the lattice. And to specify what that specific configuration is, we can use this particular state space notation to denote it. And what sets the geometry of the lattice is you can see the constraints of the molecule itself. So all of the phosphorylation space can then go from being nothing is phosphorylated, so that's 0, 0, or all of them are phosphorylated, and so that's 6 by 6. So the full phase space of this lattice or of this molecule is actually from 0, 0 to 6 by 6. I just didn't draw that because it would be too big to visualize in this slide. But that is what provides the constraints for the geometry of this lattice. Was that your question, Eugene?
Yes. So this is not an infinite lattice, but only a finite one.
Exactly.
And is
Yeah.
this lattice under periodic boundary condition or open boundary condition?
It's definitely open.
It's open?
Yes. Sorry?
So it's open boundary condition?
Yes, it's open.
I see.
My
Yeah.
question, yeah. So since open boundary condition, but what kind of system size are we looking at? Like that means like 10 unit cells or like 20 or 5 or
Yeah, so it goes from 0, 0 to 6 by 6. So 7 horizontally and 7 horizontally, 7 unit cells in each direction.
so this limitation of 7, is it because there are like 6 sort of molecules in one ring or something?
Exactly. So the index goes from 0 to 6. Exactly.
Oh, thanks.
Sure. Yeah, and I think that you're hitting on some very interesting points here, which is that here these systems are not big at all, definitely not in the thermodynamic limit that we're used to. So here we see that's why questions like stochasticity plays a big role. We cannot just say law of large numbers and therefore therefore we know what happens on average. That's not enough. And here fluctuations are very important, and stochastic thermodynamics becomes very important. And so it is really interesting now to look at what we can say for these smaller systems, because you can actually say a lot for these systems, because here we still have a state space of 7 by 7. That's still a reasonable amount. And I'm going to show later how for smaller systems we can still characterize these systems very well. But so for people who are used to lattices, this is a square lattice. Actually is even better. It's SSH. It's a 2-dimensional version of the SSH model, because here you can see that there are these sort of like intracell hoppings and these intercell hoppings. And so for people who are familiar, you can already guess what happens next. This system has a topological transition between the trivial phase and the topological phase. And the trivial phase happens when these intracell transitions, these black rates, are smaller than these gray rates, in which case the system will sort of undergo diffusion. And you can see this simply because we have clockwise cycles and counterclockwise cycles that are roughly of equal amounts on this lattice, so they're roughly balanced. So just by inspection, you can see that the system, when these black rates are slower than these gray rates, the system will just wander around the lattice, and then it will just explore the space of the lattice, and then in time it will ergodically explore the whole phase space. And so this is just 2D diffusion along the lattice. This is the most ordinary vanilla thing you would expect in biology, nothing very exciting. But there is also a different regime, and that happens when these black rates are faster than these gray rates. And you can see that, again, by inspection, what happens. And this is something that I enjoy very much in these sort of classical or stochastic topological systems, that we can actually see the topological dynamics by eye. Because what happens in this case is that instead of just 2D diffusion, the system will undergo 1D ballistic motion on the edge. So we can see this just by looking at it. Let's say the system wanders here to the edge. Here it can only move forward. Now in this case, remember that the black rates are now faster than the gray rates. So this is going to be more likely. It can only go here. Now this is more likely. It can only go here. And then it has to turn the corner. This is more likely. It has to go here. This is more likely, and so on and so forth. So now it will just go around the edges of this lattice instead of wandering. And so of course, this transition between 2D diffusion, which is much slower, to 1D ballistic motion is very interesting. And what is also nice about the system, this model, is that it inherits the properties of topology that we love, which is that the system is robust to, let's say, if there's missing states, let's say there's some kind of a lack of reactants, lack of chemical bonds that it can access. Then in that situation, instead of having this edge state just hit a roadblock and then fall away and dissipate back into the system, here into the bulk, here you can see that now here, if these sites are inaccessible, then here it will round the corner. This is more likely. This is more likely. Here it has to go here. Then it has to round the corner, and this is more likely. So that in time, it is going to just follow the maximal available lattice space that it can, and go around whatever available edge there is. And so this is really a very nice property, because this can speak to the question we had about robustness of biological phenomena. So how does development happen even when there's many changing stimuli or changing environmental conditions, and yet the system can still pivot towards its goals and towards what it wants to achieve. So this is one idea of robustness that is very attractive, for which we don't really have good theories, especially when it comes to large, complex systems.
Actually, I have a question.
Mhm.
So my question is that okay, so just now you mentioned SSH topology, but in this case, if you're talking about robustness along the edge, it looks more like Chen topology. So like which one is it?
You mean because it's more like a quantum Hall kind of state?
Yeah.
Let's see. Yeah, you're right that here, instead of like the 1D SSH chain where it is fixed as edge states and localization, here we're actually getting a current. Here I would say that there is some symmetry classification here, that this is using invergent symmetry. So also invergent symmetry doesn't quite fit into. I would say that either of the descriptions are probably appropriate. And in some sense, one can think of a churn, can think of the Hall effect as being the continuous version of an edge state like this in two-dimensional space.
Sorry. So I'm also wondering about something else. So because in this case, right, the state space is actually more like about the occupancy of the molecules at 3, 4, or 3, 5, or this. So is there a reason why this lattice is supposed to be translation invariant, or is it actually not translation invariant?
Yeah, so here the translation is the chemical bonding. And what we are saying is that here that adding one phosphorylation is the same as adding two phosphorylations, the same as adding one phosphorylation is the same as adding the second phosphorylation, as the same as adding the third phosphorylation, etc. So this is sort of, I would say, the simplest model that we can have. Clearly, one could start to vary this. One could imagine other scenarios in which adding chemical reactions maybe starts to slow down after a while. So what is very nice here is that instead of in solid state systems, we just have hard boundaries given by the size of the lattice. Here we could have soft boundaries. That's actually something that I'm writing a paper now with my student Chong Bin, who I think contacted you about, because we see, like, for microtubules, these filaments that grow and shrink, that you could have soft boundaries that does start to break translation invariance.
Thank you.
Thank you, Jinghua. And so here, this is really something that's very nice, and that we can look at this robustness, and that does draw from the classification of topological states, as also as Jinghua was asking, that has roots in random matrix theory and looks at the robustness to random perturbations. And what is also nice from the biological system's point of view is that we have this large lattice with a lot of phase space, but in this very simple limit on, in this very simple assumption of having this translation invariance, we really have this repeated rates. And so this very large state space of rates can then be described very simply by these two rates. And so this simplifies very much the phase space of the system, which is very helpful when we want to make predictions for experimentalists, instead of having 20 parameters, all of which can be varied, so that we don't really know which one is the most crucial. But I want to stop here and just see if there's any other questions, because this model is really what we're going to be using then to describe how we might apply this to biological systems. So I want to make sure that everyone is on the same page before I move forward. So if there's any questions, let me pause for a second.
Yes.
Can I also ask a question?
Yes, of course.
So can you really design some control experiment to tune the system parameter to see the transition, the topological phase transition here?
Potentially. So for example, I had said that the topological transition here depends on the ratio of these black rates to these gray rates. And that means that the strength of these rates can be tuned for, and the strength of these rates actually depends on the chemical potential in the system. So if we feed in more ATP, for example, then that can really help to speed up the black rates. And if there's less ATP in the system, so ATP is what I had mentioned at the beginning about this chemical fuel that our systems store up, that our bodies store up. So when we eat food, they store chemical energy in the form of ATP. If there's a high reservoir of ATP in the system, then that can drive these rates faster. And if there's low levels, it can drive it slower. So in experiments, experimentalists can control the amount of ATP in the system, for instance.
Oh, that's very nice. Thank you.
Yeah, sure. Are there any other questions? If not, let me show how this could be.
Sorry, can I ask a question? I think
Yeah.
my microphone is off. Yeah, very fascinating beginning. I really like where this is going, but just in case I'm gonna get lost in a little bit. So what is the entropic? Are you gonna talk maybe later on about the entropic consequence of this? Because it feels like there is some additional, not quite like configurational entropy that's within the system that could just be hidden forever and maybe be inconsequential. But does unlocking and like sort of studying the details within here have some entropic, does it actually factor into the free energy in some way? Not that we're talking about equilibrium thermodynamics and it's important at all.
So are you saying, so definitely this is a strongly energy consuming system. So entropy is definitely being produced all the time. So you're right that that is an important part of the system. So the system is consuming energy and entropy is being produced. Is that what you were asking, or what exactly is your question?
Yeah. So for example, there's some systems in biology that are like suffer this entropic force, right? So it does, like, for example, like polypeptides and so on and so forth, their behavior cannot be solely understood without understanding the entropy term. And so I was just wondering if this system has sufficiently large entropy that maybe it'll be governed mostly by the entropic term that you're describing. Or maybe this is really going in a very weird tangent.
So when you say things like polypeptides or polymer systems in general, those are usually governed by their mechanical entropy, because these are polymers that can twist in a lot of different configurations.
That's
Here,
right.
the entropy in these systems, as they are drawn, is really there because of this chemical potential that I had mentioned, which is really what allows there to be this non-reciprocal force. Because a lot of times the large mechanical entropy in polypeptides, for instance, that is still a floppy system in which forces are roughly balanced. So any kind of twisting, there is still reciprocal. If you can twist one way, you can twist the other way. Here, and so those configurations are roughly equal. This is really a kind of a driven reaction that is dissipative by nature, and that dissipation is a more of a chemical driven dissipation that is of a different kind of entropy than the entropy you're speaking about. Does that make sense?
Okay, yeah, I think that's starting to click a little bit. Thank you.
Cool.
Evelyn, just to make sure, in your answer to Qinghua's previous question about translation symmetry, did you say the translation symmetry is just some assumption here, but it's unnecessary? Or is it necessary?
What I was saying is that in this simple lattice, you can see that, well, it is modeled that all of the rates are the same. So this is the assumption that we make here. For a real biological system, this is not a necessary assumption. And then the question becomes, how do we develop tools for systems that are not translational environment, which we are actually working on also.
So regarding whether the theory, whether the topological consequences apply to systems without translation symmetry, do they apply? Or we are or not?
I think it depends, and we are honestly taking baby steps. Well, first and foremost, there are tools out there just in general where such as real space topology, or topology for disordered systems, where people can look at, instead of K-space. I mean, the nice thing about translation invariance is that then you can go to momentum space. But if we don't have translation invariance, one can also define topology in disordered systems by looking at real space topological invariance. And so you calculate, is there some kind of, real space Chern number in local parts of real space? So there are different ways also in quantum condensed matter to analyze these systems. Here when I was talking to Qinghua, I was saying that perhaps translation invariance in our case is weakly broken, and one can also develop tools to study that, and that's something that we are working on.
I see. Also, maybe just one comment. I think your picture, it looks like I think the reason you said your picture looks like a two-dimensional version of SH model is because you have some strong bounds and weak bounds. But your picture also looks like the network model for quantum Hall plateau transition, which does have a lot of disorder, and there's also robust topological phenomena, at least in the quantum case.
Yeah, that's an interesting connection. So you're saying that so in those cases, is it at the point where it's transitioning between two plateaus?
Yeah, for example, transition between a trivial insulator and a quantum Hall insulator in a disordered environment. And a model describing it is the Chalker, what's the name of the other one? Chalker-Cartington network model? Yeah. Yeah, your picture looks like that model as well.
No, I agree. And I think it would be fun to look at the more formal similarities between them. And so if you guys would like to chat about that, I would be happy to. I mean, yeah, I agree with you.
Sure, thanks.
Great. So now I'm just going to show how this could be describing a system in biology, which is the Chi-ABC system, which describes the circadian rhythm of cyanobacteria. So cyanobacteria are some very primitive bacteria that do need a circadian rhythm. So a 24-hour cycle in order to know when to reproduce, when to eat, when to sleep, etc., when to replicate. And in fact, if the circadian rhythm is broken, then their fitness level goes down. And how their circadian rhythm is regulated is by these Chi-ABC molecules, which are hexamers made of 6 monomers. So now you see why I drew my molecules in those ways as well. And each monomer has 2 phosphorylation sites, T and S. And by day, all the T sites get phosphorylated, and then all the S sites get phosphorylated. And then by night, all the T sites get dephosphorylated, and all the S sites get dephosphorylated. There's also other ligands like Chi-A and Chi-B that can bind and unbind at different points. And also there's these A loops that can be buried or exposed. So different configurations. So actually it's quite a large chemical configuration space because of all these bindings and unbindings that can happen, different conformations that can take place, and also S and T can bind and unbind. So given this very large state space, why does such a global and robust cycle emerge? And this question is even more surprising if we look at what one might expect, which is that we expect monomers to phosphorylate and dephosphorylate independently, single monomers, and for single monomers to bind into hexamers and unbind into monomers again. Recent cryo-EM data has also shown that monomers in the same hexamer can take on different conformations, so that A loop that I showed you that can be exposed or buried, that they can also actually have different monomers in the same hexamer can be either exposed or buried within the same hexamer. So it looks as if monomers can have their own independence dynamics, and they don't have to act all in a concerted manner. So the question is, why do they act in a concerted manner? Clearly, it's very convenient for the cyanobacteria then to have this very strong wave of phosphorylation and dephosphorylation that helps it to understand when is day and when is night. But what actually are the underlying chemical reactions or networks that makes it so that it undergoes this concerted cycle while also showing so much individual variability of the monomers? So to model this, we are using our model here, where now the orange and pink phosphorylation are given by the T and S phosphorylation model, T and S phosphorylation respectively. And here we've also added reverse rates for thermodynamic consistency, even while keeping the chirality of the cycle the same. And here now we can identify that these rates can take place, let's say, by binding of Chi-B, unbinding of Chi-B, here by the promotion of Chi-A as an enzyme. And we can also identify that these different conformations can describe the exposed and buried A loops of the different monomers. And putting all this together, this is exactly the same lattice as what we had, just now with the reverse rates, but the same chiralities still dominate. And so then this would when these solid rates are larger than these gray rates, still give us a topological phase. Of course, we wanted to look in the literature to see if there's, to compare how consistent these assumptions are with the literature. And what we can see is that indeed Chi-A binding is expected to promote phosphorylation. Here going out vertically. Here Chi-B binding is expected to promote dephosphorylation, and Chi-A binding here does tend to happen to the exposed A loop. There's also another piece of our model that's needed. I had said that these black rates need to be faster, and one also sees that we expect a difference in transition rates because phosphorylation reactions are driven by ATP binding, and so whereas some of the other transitions are just diffusion mediated and are expected to be slower. So putting all this together, what happens is that in our topological state, then the system undergoes all of T phosphorylation, all of S phosphorylation, all of T dephosphorylation, and all of S dephosphorylation. And this ordering of T and S and then T and S going away just comes out very naturally, even though here we just have, two rates, the gray and the black, and we don't have to put it in by hand. And instead, in other models, here this has to be put in by hand. This is a cycle in another typical model that assumes concerted binding. This is just modeling one of the phosphorylations, and so in fact the ordering of turning T on and then turning T off, turning S on and turning S off. In other models, you have to have many more parameters, like 20 or over parameters, because you need to switch things on and off at the right time. And getting that timing correct is generally very difficult. Whereas here, the T and S ordering and dephosphorylation comes about very naturally without having to sort of engineer this one at a time. And also here you can see that here one needs to put in by hand that these rates are faster and these rates are slower. And here again, we don't have to put in special rates for the bulk and the boundary, but because of the topology, the system naturally goes on the edge of the system. Actually, it was I was at a non-Hermitian workshop last week, and someone pointed out, well, this is the critical skin effects, essentially to say that this is a system that is very sensitive to, let's say, if any of the bonds were to break or if anything happens. And typically, if we assume that a lot of cycles, and as many cycles in biological systems are modeled as, these kinds of cycles, these are very non-robust. Because if you just have some kind of break or some kind of short circuit, then you don't get the whole cycle immediately. Whereas these kinds of models, that even though it looks as if it's quite energy intensive because it consumes a lot, but then it gives a very robust cycle. And in fact, if you look at estimates, current estimates of what these kinds of processes cost, normally the actual experiments show that the energy consumption is the measured experimental energy consumption is way higher than what theorists predict. And so there's a huge energy budget and energy consumption that's going on that we don't really understand why this is the case. And here our models suggest that this could be because this gives robustness to these dynamics. So let me pause here and just see if there's any questions before I continue. Okay, great. If not, I will keep going. I've already gotten some questions about entropy production. And so here we can actually calculate entropy production as a function of our driving force. So the strength of these black rates, these forwards, the reverse rates, for example, that are driven by ATP. We can compare that to coherence. And again, for these sort of typical unicycle kind of models, what we see, and in fact, generally, this is the model free bound. In general, for any given coherence of the system, a coherence measures how good of a clock is any clock. How good of a clock, the performance of the clock, for a given performance of a clock, one requires a certain amount of entropy production. And so these are related. One needs to feed in energy into the system in order to drive a clock. And so in our system, which is described by the master equation, where here P is this probability vector of all the different states, all the different sites in the system, and W is describes the arrows, the transitions between the different sites. You can calculate coherence by the ratio of the imaginary to the real part of the first non-zero eigenvalue. And we can look at this in our system, and what we can see is that as expected, as we increase in the topological phase and the driving coherence increases, but what we get is this very curious result where as we start to drive the system starts to go more on the edge to form this edge state. And then because there's many fewer states on the edge compared to states in the bulk now, the total entropy production actually drops. And so even while the entropy production on the edge drops, but since the bulk is larger than the edge, so there is this non-monotonic behavior. So we actually get this cost precision trade-off where we get a more precise clock, even though we're driving the system less. So this is actually one unusual feature of this topological model.
Sorry, Evelyn, can I interrupt? I feel I'm getting a little bit lost because this is really interesting to me. The thermodynamic force mu is not the chemical potential mu usually, right?
It is. It's not this. I mean, it is a similar idea. It is looking at the ratio of how much are things being driven in one direction versus being driven in the other direction.
So it's like a ratio of chemical potentials between in and out kind of thing?
It's very similar to that, or like a log of a ratio, something like that. Yes.
Is there some way you can help me understand like more intuitively, like maybe in the biological setting, like how do I want to think about this mu?
It's really, potential energy. So if you think, even just if you think of a hill, and there's a hill and there is the ground. I mean, if you raise something in space, then it's going to be at a higher potential. And here, chemical energy, if you just have a huge reservoir, let's say, of ATP packets, so that even a chemical reaction that's unfavorable can be driven so easily because there's just huge abundance of ATP. And this is amazing thing about the body and the biological systems is that we often have lots of stores of chemical energy at very high levels that are ready to be released at any moment. So even in the brain, for example, as I'm thinking, as thoughts are going through, there is this very high store of energy that's just rushing in every time an action potential fires down a neuron. And so this is what really keeps biological systems going, keeps the clocks moving, keeps the neurons firing. And so there's this, sort of energy that's there all the time, because if things were in equilibrium, then things would stop moving, things would be in stasis. And instead, biology is always moving.
Okay. All right. Thank you.
Sure.
Excuse me.
Sure.
Excuse me. Yeah. I want to ask about what is this coherence?
So coherence is describing how good of a clock it is. Essentially, if you have a perfect clock, then it will come back to itself at the same time after every cycle. But these are stochastic systems. Again, we have small numbers of molecules, so every time this phase is going to be a little bit off, a little bit off.
I see. Thank you.
Sure. And more formally, to look at how we actually try to understand the topology, drawing from our experience in quantum systems, here what we make use of the fact is that the master equation looks very similar to the Schrodinger equation. And so then we can use many of the ideas from band topology that are simply obtained by looking at this Hamiltonian, where the eigenvectors of the Hamiltonian can tell us whether, depending on the winding around the Brillouin zone, whether or not the system is topological or trivial. And so here we're really exploiting the fact that the system has this translation invariance, and we can write it as a lattice, alchemical systems, and therefore we can go to Fourier space and we can look at the winding of the eigenvectors. Because here you see that if we map the master equation to the Schrodinger equation, that they're basically the same except for a constant, which means that this constant changes the eigenvalues by this constant, but the eigenvectors are the same. So whatever we can conclude for the same lattice governed by a Hamiltonian, we can conclude the same thing for the master equation.
Question?
Yes.
So I think in the master equation, P is a probability, so P is always non-negative, right? But in the Schrodinger equation, the wave function sometimes may have to be complex. If that's the case, can this analogy really work?
So you're right. So right now we've mapped things using the SSH model where all of the entries are real and when W is all non-zero, is all non-negative entries. And you're right that probability here we would just look at the probability and its absolute value, whereas here in psi we would take actually the amplitude square. So there are differences between them. So what I wanted to say is that here we can map the eigenvectors quite directly, but you're right that there's other constraint. There's one more constraint on this that really enforces, let's say, the presence of a steady state that I will get to, or we'll get to if I have the time in the last part of my talk, that does really enforce, I suppose, the presence of a steady state. So the interesting thing here theoretically is that there's some differences, some similarities. Clearly, there's enough similarities to get topology, but there's also some formal differences, which is really fun for my group to be able to figure out these very fundamental, novel theoretical aspects.
Thanks.
So let me try and go there unless there's any other questions, just so that I can show a little bit. Eugene, how long should I talk for?
It's supposed to be 1 hour.
Okay. So do you want me to stop earlier or I can just talk until 1 hour?
Either way.
Sure. I mean, I feel like I'm getting questions along the way. So yeah, clearly I'm happy to answer questions already. So here we can also simulate the system. And so in our two-dimensional space, you can see that this can just, it goes around. And here in this 2D space where time is in the vertical axis, you can see that very quickly it hits the wall and it can start going around, so that even if there's transients in the bulk, in the long time limit, the steady state will be on the edge. And here, this goes back to the initial questions I got about, well, what happens since it's such a small system? Because one might ask, even in a very small system, one might worry that the edge states can then start to interfere with each other, can start to bleed into each other. But what we can see is that at least in this strongly chiral case, the edge states are exponentially localized, so that even for small systems, even 2 unit cells across, you can see that the edge states still stay on the edge quite nicely. So that these tools can be useful even for these chemical systems that sometimes can be very small.
Wait, 1 second. So in the quantum case that I'm familiar with, how localized the edge states are is determined by something like how big the bulk gap is. What is the analog of the bulk gap here? Or in other words, what is suppose the system is infinitely large, what is the intrinsic parameter that determines the extent of the edge state?
One can also look at the gap in these systems, because you can also analyze it in the periodic limit as well. And again, there the gap will be given by some function of the parameters, and that will also determine the stability of the system.
I see. So by tuning the parameters so that that gap is big enough, then even for small enough system, the edge states are still at the edge. That's the statement.
Yeah, and in our paper on Kai, so my student Changbin, we did actually propose the gap as being connected to coherence, because exactly in these chemical master equation systems, people don't normally think about spectral gaps, especially not in Fourier space. And so here we show that the gap actually does it is a very good indicator of the coherence. So yeah, that's something that we did in our paper as well.
Thanks.
Excuse me, a related question. Yeah, so for topological states of matter, we have bulk edge correspondence. We know that we can use chiral edge modes to probe the bulk property. So can we do the same here?
So what I was saying is that here one can use the mapping of the master equation to the Schrodinger equation to calculate the topological invariance of the system, at least in Fourier space. So one can calculate a bulk topological invariance. What I will show in the last part of the talk is that this bulk boundary correspondence only works sometimes. So and actually it only works in a non-Hermitian limit. In the Hermitian system, actually there is something else that happens that makes the bulk boundary correspondence break down, even if one can still formally define this connection.
I see. Thank you.
Sure. So let me go there just because I think there are some questions about that. And this is what I was going to say about this necessity of non-hermiticity. And so here I just want to stress how important non-Hermitian systems are for biology, because non-reciprocal or non-Hermitian interactions happen everywhere. For example, the eagle grabs the fish. That doesn't happen the other way around. So things go one way and not both ways. And this gives rise to new physics. Specifically, I need to point out that even though we can analyze the same lattice, so we can analyze, let's say, the SSH model in quantum systems and the SSH model in stochastic systems, and the lattice has the same operator only under periodic boundary conditions. And this is because the master equation operator actually has two parts. One is this as an off-diagonal hopping, and this off-diagonal hopping looks the same as a tight-binding Hamiltonian. So it is describing what would be the hoppings between different sites, or here the rates of transitions between the different sites. So this A is the same as a quantum Hamiltonian. But the master equation operator has also this other diagonal term, and this diagonal term enforces probability conservation. And so if A, let's say, describes all of the outgoing rates from a different site, then D will be the sum of all outgoing rates for that site, and then we subtract that so that across all rows, now the in and out, incoming and outgoing rates have to sum to zero, and this enforces probability conservation. So since this is a diagonal matrix that is just the sum of all outgoing rates, for the SSH model, for example, then and under periodic boundary conditions, then this diagonal matrix is simply proportional to the identity because there's equal incoming and outgoing across every single site of the system. Being just proportional to the identity, this just shifts the spectrum, and therefore there's no change in the eigenvectors. But with open boundaries, then the ends of this diagonal matrix will be different, and this has huge consequences. So just looking now at this simple 1D Hermitian SSH model, we can see that, well, firstly, there is this shift. So the quantum spectra A has this particle hole symmetry around zero. And so two bunches of continuum states and one zero mode in the center. The stochastic system is shifted because of this D. So you can still see the same bunches of continuum states, but now there is no longer this zero mode. And in fact, the state of interest is now also different. In both systems, we're always interested in this state at zero, with zero eigenvalue, because that's a state that doesn't decay or it lasts the longest. So this is the zero mode in this system, and this is the steady state here in the stochastic system. And what we see is that when we compare the steady state here to the zero mode, what we see is that even for this Hermitian SSH model, we see that the quantum system, of course, has edge states, and the stochastic system is uniform. And so this is what I mean, that this breaks the conventional bulk boundary correspondence, because both of them would have the same topological invariance if we just look in the periodic system, because in the periodic system, both of them have the same eigenvectors. So whatever topological invariant we can calculate for the quantum system, we can also calculate that for the stochastic system. But clearly, this gives rise to different consequences. And so despite this, they do not have edge states. And to restore the bulk boundary correspondence, we actually need to go to the non-Hermitian system, where here we see that now going to this non-reciprocal SSH model, 1D SSH model, we see that here the quantum system has the skin effect, and also the stochastic system has the skin effect. And so what we see here is that, unlike in quantum systems, stochastic systems require non-hermiticity to have edge states, and we can prove this for any geometry and dimension. So this is very simple proof. It holds really for any system, so long as the system is ergodic, which means that you can get from one place to any other place. And so for any ergodic master equation, then if the system is Hermitian, the steady state will always be uniform. And so it never has edge states. And so actually, in order to have edge states, we actually need to go to the non-Hermitian system, and then we get back our topology. And then the bulk boundaries correspondence can be restored. So actually, so we wrote this paper describing these very interesting differences, where we see that here again, non-reciprocity has very different effects. Here you can see that the quantum state already has non-zero edge localization. The stochastic system, of course, doesn't have anything, and in fact, the quantum system plateaus quite quickly as we change non-reciprocity, and the stochastic system instead grows very quickly. And we also, in this paper, we introduced a novel mechanism for non-Hermitian systems to preserve edge states, where we suggest that the imaginary spectrum prevents edge and bulk states from hybridizing, and this protects edge states and currents by just enlarging the space in which eigen states can live. So I'm just going to close, hopefully with something a little bit fun. So here we're collaborating with an experimentalist from Rice University, Lisa Biswell, who has magnetic colloids that she then can drive with a magnetic field, and they rotate, and they form these areas of many particles, where areas of no particles, and also clusters. And we actually see edge states around these voids and these clusters, and can identify and analyze them. Here we are adapting and building on theory that was first developed for some chiral fluids in Das Biswas et al. And here we can see that these edge states then decay exponentially. And we can here now obtain different physical parameters for the voids versus the clusters, and then we can tie these edge states now to driving the system as a result of creating strong shear forces around the boundaries of the system, so they make the clusters rotate, while the voids being stuck in place cannot rotate as well. And then this gives rise to very different timescales of coarsening. So now here we see that the self-assembly of these systems are very different. Here for these clusters, they join together, and then this domain wall very quickly translates out, so it becomes just one smooth cluster. Here for these voids, after a long time, minutes, even hours, the domain walls still remain because they're stuck in place. And so we can predict these things using our analysis of the different physical parameters, and we see that these properties of these edge flows are really driving reorganization, macroscopic reorganization at very different timescales. So here, these edge states are really causing very dramatic dynamical behaviors as well that we can quantify. So now I'm just going to close, and just to summarize that here we have simple repeated motifs that here can predict robust global dynamics, such as a global clock. They can model the circadian rhythm in cyanobacteria. We can prove that non-reciprocity is necessary for edge states in stochastic topology, unlike in quantum and mechanical systems, and in most topological systems that we know, actually. And lastly, we have been analyzing how topological edge flows can drive macroscopic reorganization in noisy colloidal systems. And here, we just put out an invited review about some of these things. And I want to thank my group. So Chongmin is a student who did the work on Chi. Alexandra Nelson did the work on proving that non-hermiticity is necessary. And I want to thank my collaborators and funding sources. Thank you.
Thank you, Evelyn. Thank you for the very nice talk. I think this seminar is really enjoyable. There are many effective interactions. So do people have further questions?
Yes. Can I ask a question?
Go ahead.
Yes. Okay. Thank you. Thanks for the very nice talk. I still have a question about the difference. Can you go back to the slide where you talk about the difference between the zero modes and the steady state? I still quite don't understand why this difference for the stochastic thing, because in the quantum regime, if you calculate the zero modes of your Liouvillean, then your zero modes, assuming there's no degeneracy, then your zero modes is basically your steady state, right?
So I don't. So there is still this D operator that makes a difference. So the Liouvillean is based on a Hamiltonian. I don't think it has this flux conservation, this probability conservation term, right?
No, they don't have.
Oh, so yeah, it's this probability conservation term that's making the difference. So
okay.
that both shifts the spectrum, and also that gets rid of the zero mode, and now there is this thing at the end.
Okay. I see.
Actually, I have a question about this as well. So I understand that the reason why you say that the stochastic W doesn't have the topological modes like edge modes, right? It's just because this diagonal matrix sort of has it's not transitionally invariant at the edges, right? So So that means you don't have a usual sort of open boundary conditions for the topological modes. But I'm just wondering that is this like a very universal conclusion for all types of models, and that means all like sort of types of hoppings and all types of effective lattice models, or is it just for the particular models that were studied and a particular type of topology that were studied?
Yeah, no, this is extremely general. So we can prove this essentially for
Okay.
again any master equation system. The
Yeah.
only condition that we need, because this is using the Perron-Frobenius theorem, and the only thing it relies on is that the network is ergodic, which means that from any site you can reach any other site, which anyway, all tight binding model, most tight binding models are almost all topological models satisfy anyway. So no, this is true for any dimension, any geometry.
So that means but so that's why you mentioned zero modes. So let's say if I have topological modes that are not zero modes, then does it still apply?
So what this proof is saying is that for
Yeah,
the master equation, that the steady state is always
yeah.
uniform if the system is Hermitian.
Mhm.
It was not saying anything about the excited states. So you're saying it doesn't matter whether it's a zero mode. The question is whether the zero mode gets mapped to
Because
sorry.
yeah. So maybe I mean the thing I'm thinking about is that okay, so let's say if I have an effective model that's more complicated, let's say there are multiple bands, and in between some of these bands that could be topological modes. But of course, we don't expect the topological modes to be at zero sort of eigenvalue. And that means, and now if you talk about the stochastic version of this model, right, then of course I understand that if you're talking about the zero mode, that's constrained by the Perron Frobenius model. But I mean,
Theorem.
but if you're talking about those just generic like topological modes that are in between bands, then maybe they may not necessarily be sort of constrained in this way. Yeah.
No, absolutely. And I would say that even actually, even in the Hermitian case, if you look at the higher states, you do see that they will have some kind of edge behavior. Probably not as nice as the quantum state. So, quantum state normally they're exponentially decaying. So, but here in some of these excited states, you might see maybe like some kind of maybe more power law kind of behavior. So you'll still get some kind of topological effects, but you're just not in the steady state. So what we're saying is really only about the steady state.
Thank you. Yeah.
I have a related question. So here, when you say the steady state is uniform on the open boundary condition, by uniform, do you really mean uniform? If there's
Yes.
open boundary condition, then there's no translation symmetry. Why would I expect anything to be uniform?
Because these stochastic systems are, like what you were saying before, there is no complex hopping. Everything is real. So if this is Hermitian, this means that all detailed balance is always satisfied. So somehow everything has to, that's what happens.
Oh, okay.
It's really because of this diagonal term that makes that happen. Because somehow now things have to be, it imposes this this constraint, this conservation.
Oh, I see. Yeah, it's just due to ergodicity.
Yeah, I mean that's another way of thinking about it.
I see. Okay, any other questions?
Just a small one. So you mentioned extensions to disorder. I was wondering if interactions ever are on the list too of extensions, whether nonlinearities become important in the kind of because it seemed like a lot of these equations were linear, so you're doing a kind of eigenvalue analysis, and I was just wondering if nonlinearities play an important role.
Yeah, that's a great question. You also said something about interactions. So, and I think that maybe it's a little bit different. But you're right that interactions can normally give rise to nonlinearities. So, for example, in the binding that I was showing, that would be sort of individual binding events, and that's why we expect them to be roughly at the same rate. Once we expect, if we let's say have a situation in which we need dimer binding, so two molecules to bind at the same time, we would already expect nonlinear effects. The master equation formalism can also model nonlinear effects. Then the rates start to become nonlinear functions of, let's say, the space or the other or of the events. So it can handle that formalism. But I think if we do want to think about, but this is still the single particle picture. And so if we do want to think about particles interacting with each other, that would definitely be, that's definitely important for biology, but also, yeah, that's also would be added noise, and that would be a very interesting question of what happens there.
I see. So the interactions you care about are actually already within this formalism, it sounds like, and you can.
Well, if we think about binding, it depends on what kind of interactions. If it's interactions of binding events that happen at the same time, then yes, we can include that. If we're thinking about one model interacting with another, one system interacting with another system altogether, so one SSH model interacting with another SSH model, those kinds of interactions, so that it becomes not just a single particle system, but a more of a many body interaction system. Then those things we cannot include. That does not come under this, and we would be very curious what happens there.
Okay.
So a few ideas, yeah.
Thank you.
Yeah, I still have a question related to what Qinghua asked earlier, which is, are we really looking at which topological class we are looking at? Are we still looking at the SSH model with chiral symmetry or chain insulate like kind of symmetry class? Or I suspect this might belong to one special case and this extended non-Hermitian topology classification. So I'm not sure. Maybe Qinghua also has some thinking already. So I'm wondering, what our speaker might have in mind.
Yeah, so for sure, in the stochastic systems, we have to use a non-Hermitian everything. And so it would also be some non-Hermitian extension of the Zach phase, for example. So now we have to use left-right biorthogonal basis. And but I think it is still a Z2 invariant for our model.
Yeah,
I mean,
but spectrum you presented, right? You do use Z2 class to
yeah, but it's definitely an open question about what is an appropriate classification, because here you can see that, right, this breaks the boundary correspondence. We do have to understand what happens within these constraints that are here. So that is a very interesting open question.
Thank you.
Yeah. No, great questions.
Any other questions? Okay. If not, we can close today, and let's thank Evelyn.
Thank you.
Thank you.
I believe
Thank
you
you
can
so
hear
much.
me. Okay. Yeah, thanks. Bye.